Yes, yes.
or because it is just a simple, very simple law. We can just go very quickly through these slides. It is the just mathematical calculation of how much how we can parallelize our code, or how much advantage we can get by parallelization of our code, right? So it was formulated in 1967 by the scientist Amdahl. So basically, in the previous slide, we have discussed a most part of this, that we have to convert our code. If we run our code into the serial mode, it can run on the multiple. If we want to run it on the multiple cores, we can use two different approaches, right? One approach that splits the original computation over the additional cores to reduce the program runtime, right? And second approach is to use the additional number of cores to solve the scaled up version of the original problem. Now, Amdahl's law, it basically implies a limit on how much faster you can solve the original problem by using the additional cores, right? An unparallelizable portion of the program limits performance of the code, but it is more detrimental when the problem size cannot scale with the number of cores. So basically, Amdahl's law, it shows that program serial parts limit the potential speed up from parallelizing the code, right? Basically, as we discussed earlier, Amdahl conceptualizes the programs into two parts, right? One is the completely serial part, and second is the completely parallel part, right? Serial part, we have denoted it as Fs, and the parallel part as the Fp, right? Now, when the program executes on a single core, that is in the serial fashion, its execution time is say t1 will be sum of the time, total time. If we our whole application is running into the serial mode, then total time t1 will be of fs, that is for serial part, and time spent executing the parallel function part fp. So presently we are executing all of our program on the single core, that is in the serial fashion. So serial part is taking time fs and parallel part is taking time fp. So total time will be fs plus fp, right? So when the program executes on multiple cores, for example, if we use GPU, we are using multiple cores, the computations in the parallelizable code sections are divided among the available cores. So our whole of the program will be divided among the cores. Now the serial part cannot be, but this by even if we parallelize our code, serial part they will execute in the same way. It will still take the time fs only, but the parallel part, as we have divided it into the number of n cores, so the time it will be divided in by n. So total time now will be equal to fs plus fp divided by n. Now, as the number of cores n increases, the total execution time will approach the serial portion of the code, because we can see that as n increases, fp over n will reduce, and eventually it may become zero also. So it will mainly then depend upon fs only. Of course, theoretically it can be zero, but practically it can never be zero. So diagrammatic representation, we have a serial part of our code, and then we have a parallel part of our code, of our task, right? Now if we increase the number of cores of our parallel part, where here two cores, then we have four cores, then we have eight cores. So this length represents the time. So we can see that as we increase the cores, the time is reducing. Here the time is only this part, right? There is no effect on the serial time. There is the effect only on the parallel time. Parallel time is reducing as we increase the number of the cores. Now, according to Amdahl's law, running your application on a cluster cannot decrease the total parallel running time to zero, because the serial portion cannot be accelerated, because a serial portion puts the limit on our efficiency enhancement of our code, because it cannot be accelerated by increasing the number of cores. So the execution time of the serial portion determines the lower limit of the runtime. Now we can mathematically represent this whatever we discussed. To simplify the later expression, we can define the single core execution, that is serial execution time, as 1 unit of time. Let's say fs plus fp, we put it as 1, right? Expressed in terms of speed up. This we have done to calculate the speed up. S. Amdahl's law says that speed up S is equal to serial runtime divided by parallel runtime, right? That is the speed up. Serial runtime, as we have calculated in a previous slide, that was T1, and parallel runtime, as we have calculated, was Tn. Serial runtime fs plus fp, and parallel runtime we have seen fs plus fp by n, that is parallel part divided by number of cores. So whole this fs plus fp, we are putting it as 1. Then this is the speed up we are getting. So now as the number of cores increases, the serial portion dominates the execution time. That is, if we, let's say, if we put the limit on this, if we put the limit on this, that as limit n approaches infinite, then the speed up s is equal to fs plus fp by fs, that is equal to 1 over, we can see just in this diagram, as n approaches infinite, fp over n will become 0, so we will get only 1 by fs. So as long as fp by n is large as compared to fs, speed up is proportional to the number of cores. So in our this equation, if this second part, that is fp by n, is larger as compared to fs, then only we can uh, increase efficiency by increasing the number of cores. It means that the most part of the code is parallelizable. That is, we can increase the efficiency of our code if our code is parallelizable. If our code is not parallelizable, then we cannot increase its efficiency by increasing the number of cores. Therefore, it is only when that fs is much smaller than fp that it is appropriate to use more cores. As the number of cores increases, the execution time will approach fs. Adding more cores after this point will not yield any additional speed up. So now if we talk about in terms of GPUs, about this Amdahl's law. Now, before we can dive in and unlock the potential of GPU, we first have to realize where their computational power lies in comparison to the modern CPUs. Right? The power does not lie in the higher clock speed, nor in the complexity, not in the particular design of the cores. Power lies in increasing the number of cores which the GPU does. Okay? As just like a GPU core is actually a quite simplistic and at a disadvantage when compared to modern individual CPU core, which uses many engineering tricks such as branch prediction to reduce latency of computations, etc. But GPU cores are very simple, but their power lies where because they are huge in number. They are a lot of number of cores, which increases the throughput or the efficiency. So now coming to the term throughput, the power of the GPU derives from the fact that there are many cores than in the CPU, which means a huge step forward in the throughput. Now, throughput basically it refers to the number of computations that can be performed simultaneously. So, I think regarding throughput and parallelization, basically, we can get an idea of the increase in throughput by seeing how many cores these new GPUs have. For example, average that we have seen that average Intel GPU it have 2 to 8 or 16 cores, but many GPUs they have different cores like 640 cores at the entry level, and the top of the line NVIDIA RTX 2080 Ti it has 4352 cores. So we can see that we can exploit massive throughput, but we must see that how properly we can parallelize our program or algorithm we wish to speed up, right? So so by parallelize we have to first find parallelizable portion of our code. We have to see that which part, of course it is if we are processing a huge array, then and we are performing the same operation in different elements of array, that is single instruction multiple data, then of course we can parallelize our processing of different elements of our matrix or of our array, right? So it means that we have to rewrite program or algorithm so that we can split up our workload to run in parallel on multiple cores simultaneously. That is, we will have to rewrite our program in the parallel for achieving parallelization. So this is all about the Amdahl's law. It just gives us the rough idea, rough estimate how potential speed up that we have seen in the mathematical equation, how potential speed up we can achieve by making our program parallel. So this just give us a general idea as to whether it is worthwhile to write a parallel version of a particular serial program, provided we know that what portion of our code we can parallelize and on how many cores we should run our parallelized code. So these are the two parameters. We have to see that what is the portion of our code we can make convert into the parallel version, and how many number of cores or what processor we need or how much speed up. Of course, if we need a higher speed up, we have to use the GPU of higher configuration. So based upon our requirement, we have to use the GPU. So this was just a theoretical concept that is about regarding Amdahl's law. Just gives the idea that how much efficiency boost we can get by parallelize over code. Now coming to the next slides. Now we just go into quick start of CUDA C. Now we are in position to start our CUDA C programming. So I'm starting with the slide of introduction to CUDA C and C++, right? So I will just skip the part if any, and if there is any repetition in this, if we have discussed that concept in the previous slide. Should I go ahead with this? Yes. Anyone having any point to discuss?
Yeah, Vikram, we can go ahead.
Yeah, fine. So CUDA programming model basics, as we have discussed in previous slide also, we have here just reviewing once again, as we are just going to start with the programming part. As we are just I will touch the main parts. We must know what is CPU, we must know what is GPU, what is meaning of host. CPU is referred to as host, right? And The host so refers to CPU and its memory, and device refers to GPU and its memory, right? Code runs on the host can manage memory on both host and device. The code will run on the host, right? Our main function, our main program, main function will execute on the host, right? So it can manage memory. Our host code can manage memory on both, that is host as well as device. Host launches the kernel, which are function executed on the device. These kernels are basically executed by many GPU threads in parallel. So basic CUDA operations. Now, given the heterogeneous nature of the CUDA programming model, a typical sequence of operations on a CUDA C program, as we discussed earlier, also typical sequence of operations will be: number one, to declare and allocate host and device memory. We have to allocate, declare first, and then allocate host and device memory, right? Then we have to initialize the host data. Then we have to transfer the data from the host to the device. Then we have to execute one or more kernels, that is GPU computation. Then we have to transfer back the results from the device to the host. Now, regarding the host memory allocation, you might, all of you might be aware of using the function malloc. Normally, we'll be using the malloc to assign the for allocation in the host, right? So the malloc, that is memory allocation function method in the C, it is used to dynamically allocate a single large block of memory with the specified size, right? It returns a pointer of type void, which can be cast into a pointer of any form. It does not initialize memory at execution time. So it is just assign allocation is done. There is no initialization done. It has initialized. So there is the garbage value. It will. It may. We have to initialize with the useful values. By default, it will hold only the garbage values if we use the malloc function. As the syntax for host memory allocation, we can use the syntax of a pointer where the value pointer to the that block of memory, and we can type it, cast it to any particular type, and then malloc, and then how much memory byte size, how many number of bytes we have to allocate. For example, integer star pointer, we have declared a pointer to point to the integer type of the memory, and ptr, we have ptr is assigned a value by malloc. We have cast it to the integer star because we want integer block of memory. Malloc, let's say we want to reserve the 100 elements, for 100 elements multiplied by size of integer, right? Now since just a second. Now I think color is a bit dark. Now, since the size of integer is 4 bytes, this statement will allocate 400 bytes of memory, and pointer ptr will hold the address of the first byte in the allocated memory. So this is, we have this is the function to allocate the memory in the host. Also, we can allocate using the new operator. We can allocate the host memory through new operator also. What is its syntax? Whatever is the data type. If everyone is aware, then I can skip this slide of this using such basic operators. Please let me know if this is the case. Now syntax, data type, which type of data type pointer we want to create. Star pointer name and is equal to new data type for single element. and data type star pointer name is equal to new data type and number of elements. For this is for multiple elements. So from the examples we can see that integer star I is equal to new integer. For we have reserved a allocated the memory of type integer and the pointer name is I. Similarly, we can create a float type pointer and memory allocation by using the new operator over here. Similarly, we can do can for the class objects also. For example, the complex C, if the complex is a class and C is object of type class, and we can create its object using the new operator. Now, use of new operator to allocate a block of memory, which we normally require in CUDA application, because we have to work into large size arrays. Or so integer star ptr is equal to new integer 20. So this statement will dynamically allocate memory for 20 integers of type integer type int. So you can see that total size will be 20 into 4, 80 bytes. So PTR, this statement will reserve the 80 bytes if the size of one integer is 4 bytes, and it returns a pointer to the first element of the sequence to the PTR pointer. It returns a pointer to first element of the sequence to the PTR pointer, right? So we can use malloc or new operators for this. Similarly, for deallocation, we can use a simple function that is delete. If the pointer variable is pointing to the single data object, then we can use the statement simply delete pointer variable, right? And if we want to free the dynamically allocated array by the which was allocated using the new, then we can write delete, and then we have to mention the square brackets and name of the pointer variable. We can deallocate the host memory using the free keyword, right? So free function in C++ deallocates the block of memory previously allocated using malloc. Delete is used to deallocate the memory which was allocated using new, and free for to free the memory which was allocated using the malloc or calloc or realloc functions. But presently in the subsequent programs we'll be using malloc only. So it is freed so that it is available for further allocations. The free function does not change the value of the pointer, that it is still points to the same memory location. Pointer will still point to the same memory location, but it will be freed. Void free, the syntax is, for example, we use free x. The syntax is return type is void, free is the name of the function, and the pointer whose memory allocation has to be deallocated, free x. Now we come to the CUDA API functions. These are the device functions. Now CUDA API functions data transfer between host and device using CUDA mem copy. This is the CUDA API function to transfer the data between host to device or device to host. It is for bidirectional. It can be used for both type of the transfer, that is H to D as well as D to H. The syntax is this one: underscore host underscore. It means this function can be written into the host code as well as it can be written only into the host. This function cannot be used into the device code, right? CUDA mem copy, and return type is CUDA error underscore t CUDA mem copy, then destination pointer, then source pointer, then number of number of bytes to be transferred, and then type CUDA mem cpy kind, that is another enumeration kind of transfer, that is H to D or D to H. use is the copies the data between host to device, and its parameter, as we discussed, destination memory address pointer, destination memory address, source memory address, size in bytes to copy, type of the transfer. Now return type is CUDA error underscore T. It is an enumeration type, and it can have any of these three values. First value is the CUDA success, means the transfer was successful. If it returns 0, means there is no error. CUDA success is its literal name, and error code is 0, right? CUDA error invalid value. If the value is invalid, then it will return the code 1. For example, if we try to write float value into the integer or integer into float, or if it is character value into the integer, so in invalid value, the error will be returned. One code is 1, and literal is CUDA error invalid value. And third type of error is CUDA error invalid memory MMCPY direction. If the direction is not, if there is any error because of the direction, then error code will be returned 21. Now coming to the description, more description of CUDA mem copy. As we discussed, it copies count bytes from memory area pointed to by the source to the memory area pointed to by the destination. Now the fourth argument, that is kind of the, or the direction of the copy. It can be any of these. It can be from host to host, it can be from host to device, it can be from device to host, it can be from device to device, or last one is the CUDA mem CPY default. So default is recommended, in which case the type of transfer will be inferred from the pointer values. So the pointer, if the pointer is pointing to the device memory or to the source memory, from that it will make the decision that whether the transfer has to be from source to from device to host or host to device. Based upon the pointer types, then CUDA mem copy default has to be chosen. CUDA mem copy default is only allowed on the system that support unified virtual addressing. Uh, Calling CUDA mem copy with DST, that is destination and source pointer, that do not match with the direction of the copy. If there is mismatch between the types of DST, SRC, and direction of the copy, that results in undefined behavior, or it may return the error. The third error code, that is CUDA error invalid memory copy direction. Now another function, next function we can use for the allocation on device, for memory allocation on device. Earlier we used the function malloc for allocation on of data, memory allocation on the host malloc, and for its equivalent for CUDA equivalent for allocation on device, that is CUDA malloc. Its syntax is host underscore underscore host, means this function can only be used in the host code. It cannot be written into the device functions. Oh, sorry, it is having it is ported for device as well as for host. We can write it into the host code. We can also write it into the device code, and its return type is CUDA error underscore T, enumeration type. Error code will can return CUDA malloc, and pointer. First argument is the pointer, in which the address will be saved, and how many size of or number of bytes has to be reserved into the device. So it allocates the memory on the device in the global memory, right? Its parameters are dev ptr. It points to the allocated device memory size. It is the requested allocation size in the bytes. It returns CUDA error underscore T, enumeration data type. Its possible values can be CUDA success is 0, error code is 0, CUDA error invalid value then 1, or CUDA error memory. If there is any error in memory allocation, then it will return code 2. If there is any error, which is which is not any of above, then it will return value 2. So, brief more description. It can be used in the host as well as device code. It allocates size bytes of linear memory on the device and returns in star dev ptr a pointer to the allocated memory. The memory is not cleared, just like alloc function. Memory is not cleared. Just a second. And the allocated memory is suitably aligned for any kind of variable, and memory is not cleared. Now, equivalent to free function on the host, its CUDA equivalent is the CUDA free. Deallocation of device memory is done using CUDA free. So its syntax is underscore underscore host underscore underscore device, means it can be used into host code, also in the device code. Return type, most of the function have return type of CUDA error underscore t, to return if there is any error in the process. Name of the function is CUDA free, and we have to send the pointer whose memory has to be deallocated, right? Parameters dev ptr, that is the pointer whose memory has to be deallocated. Return type can be CUDA success, it can be CUDA error invalid value. It frees the memory space pointed to by dev ptr, which must have been returned by the previous call to any of the following functions. We can different memory allocation function. Till now, we have I have gone through only CUDA malloc, but there are many other functions like CUDA malloc pitch. We will go through CUDA malloc managed, CUDA malloc async, or CUDA malloc from pool async. These are different functions available for allocation in the device. And CUDA free can be used to deallocate the memory which is allocated by any of these functions. Uh, so this is a sample code now, a SAX-P code, that is the simple single precision AX plus Y. SAX-P means single precision AX plus Y, because it means that we have two arrays in this X and Y arrays are there. We want to process the two arrays, X array and then Y array, and Y is equal to AX plus Y. And these are multi-dimensional, single dimensional arrays, X and Y. So in the beginning of the code, we are writing simply header files are included like stdio.h, iostream, or simple any other header file we can include at the top, just like a normal C++ code. Then here we are writing the kernel function, right? With the identifier and underscore global underscore return type is void. Name of our kernel code is sexp, and its argument integer n, the number of elements of the array to be processed. Then this variable a, which has to be multiplied with the x elements, that is the single element float a. Then float star x, that is the pointer to the first array x, and float star y, that is pointer to the second array. So now here I will show these different variables. These are very important. I'll just show here, and later in the subsequent slide we will discuss its. Okay, right. So there are three inbuilt variables we are using. Block id x.x, that is the index of the block within the grid. Second, we are using block dim.x. X means x, x dimension only. So block idx.x, that is the x index of the block, and block dim means dimension of the block, that is the number of threads in the block. right? And thread idx dot x, that is the index of the thread within the block only. So I will just go a bit detail about this statement. This statement is to create the unique index of the thread, which will be used to access the element. For example, here if I have written the statement, if I is less than n, yi is equal to a multiplied by xi plus yi. Then in the main function, we are creating the first number of elements, or let's say 1 million elements. Then we are creating the pointers, x pointer, y pointer, d underscore x and d underscore y. Then we are doing the allocation of x and allocation of y using the malloc of type float. N number of elements are there. Then we are calculating here number of blocks by using this formula, like n plus 255 plus, so that at minimum one block is selected. Even if let's say n is equal to 1 plus 255, that is 256 over 256. By default, at least there will be one block. And let's say number of threads per block are 256. Just a second. Yeah. So further, next we are in this code displaying the message that number of blocks being launched, that is number of blocks, that number of threads being per block, that we have defined number of threads per block, 256. Then we have a CUDA malloc. We have called the function CUDA malloc to allocate the memory into the device. Then CUDA malloc for x and for d underscore x and d underscore y. Here we have, then we are initializing the values for x and y. By this simple loop, we are initializing the values of x and y. After this, we have to transfer this x and y to the device. That we are doing through these two statements: CUDA mem copy. Here source, it is transferred from x to d underscore x. How many number of bytes, and direction is copy from host to device. Similarly, are copying from y to d underscore y, right? Hello.
Hey, will you be elaborating a little bit on how you are configuring the number of blocks and threads per
Yeah,
block?
yeah. I will do that. Yeah,
Okay, looks like you'll cover that later, right?
yeah. That I will cover later. No issue. I will just quickly go through this code, and then we can see its further details. Here we are calling the kernel. Uh, this is the our kernel saxp kernel. This is the first argument is the number of blocks, and second argument is the number of threads per block. And then this is the parameter. Sorry, we can say this as execution parameter. The whichever values we will pass in these angular brackets, we call these as execution configuration or execution parameters, or kernel configuration, we can say this. And these this in the round brackets, we are specifying its arguments. First is the number of elements, and then the value of a, then the array device arrays d underscore x and d underscore y. So after this computation is complete, we are again we can use here to block till the time execution is complete. We can add that statement, and then we can copy the results back to the from d underscore y from device to host. So we are copying back results because y is our output. So we are copying back only y, not x. So it means there are three types of transfers. We have two types of transfer, that is x and y from host to device, and one transfer from device back to host, right? Uh, Now, just to check if any error, we have written a simple code to see if there is any error, because we know that the value will be answer will be 4, because constant value we are passing 1 and a we have passed 2. So y, that is y is equal to basically ax, that is 2 into x is always 1, 2 into 1 plus 2. So all the elements will have value only 4. So just to check the error, we have written this simple function max error is equal to max of max error. We have initialized max error initially to 0 to find the difference between all the elements of y between and 4. And if there is any error in the calculation, that will be printed over here. Then we have CUDA free d underscore x, CUDA free d underscore y, free x, and free y, right? So just more detail about this code. It is having host code, right? In the host code, we have declared two pairs of arrays, like x, y. So this is for host, and dx and dy for device, right? The pointer x and y point to the host arrays allocated with the malloc in the typical fashion. This is allocated using the malloc function. Similarly, for d underscore x array point to the device arrays allocated with the CUDA malloc function from the CUDA runtime API. So this was malloc, and this is for CUDA malloc, right? CUDA malloc for d underscore x and d underscore y. The host and device in the CUDA have separate memory spaces, both of which can be managed from the host code. Uh, CUDA C kernels can also allocate device memory on the device. Means we can create the device variables within kernel also. Now regarding the initialization of the host array, that is the simple loop to just initialize the arrays. We have created initialization part of the x and y. Similarly, for the device arrays initialization, that is that we have done using the CUDA mem cpy, right? So CUDA mem cpy, we have seen its detail. It is a standard C memory copy function, right? So we have seen its details. So initializing of the device arrays is by copying from the data from host to the device, that we have done by copying the data from host to the device, n number of bytes, and CUDA mem copy host to device. That is the direction. For after running the kernel, we get back the results from the device to the host by using again CUDA mem copy. Again, we are getting back the result from d underscore y to y, right? Kernel launch. Okay, that should be earlier slide. How to launch the kernel? sexp, name of the kernel, then number of blocks, and number of threads per block. So for this, these two, we have to see the specifications of our card, right? We can see the specification of our card, that how many number of maximum blocks are supported and how many number of maximum threads are supported per block. So we have to set these value within those limits only. and preferably they must be of the order of 2 raised to power something, so that it is because the threads are launched into the group of 32. If we do not do that, then the some of the threads will remain unutilized. So that is the main thing in this. The information between the triple chevrons is the execution configuration, as we discussed earlier. That is the number of blocks.
So,
Yeah.
hey, so here, so except besides the block numbers and also the forest numbers,
Pardon?
so can user control
Pardon?
besides the block numbers?
Yeah, precise numbers we can use. We can write.
Yeah, and also thread numbers. So could the user control the number of cores, GPU cores, how many cores used?
No, cores, that is the hardware feature that we must see on how many cores are available. But also there is specified that how many number of threads we can specify in a block, and how many blocks can be specified in a grid, like X dimension of a block and Y dimension. I think I skipped that slides. I they may be later on. I now am realizing that slides should be here only. Anyway, we will go through those slides in which I have given details of these indices. That slide will come later in some other presentation, or maybe in this presentation.
Yeah, till now, what I can see is the users can control the number of blocks, right? And also number of
Yeah,
threads.
yeah, we can.
But for cores, so I don't know. That's why I have that question.
Yeah, we can control. We can launch as many blocks as we want, and we can launch as many threads in a particular block. We can write here one also. We can just launch one block and one thread per block. So we
Yeah, of course, yeah. My doubt is the number of GPU cores.
yeah.
Vikram,
Yeah.
in addition to the block and threads,
Yeah.
is there another execution configuration that tells how many cores of the GPU that can be used? And that's the question.
No, that we can't. No, that is not there.
We
They are
have no control. Okay.
No, we don't have control. There are 4 arguments total, basically. 4 configuration parameters we can specify. Third parameter is related to the shared memory. And there is fourth parameter, I suppose, related to the this stream, on which stream it will be executed, because we can launch multiple streams, and we can specify that on which kernel, over kernel will be launched on which stream, right? So third parameter is related to the shared memory, and fourth parameter is related to the stream number, on which stream we can execute our code, right? But not on the core specifically. But stream is related to the core somehow. Internally, stream is related to the core. So indirectly, we can do that.
Oh, so stream is also a number, right?
Stream is a number, yeah.
Excuse me, I have a question. So, like, is it possible for us to launch 2 threads in our core at any given moment? So at the same time?
2 what? Pardon?
2 thread in a core.
2 thread in a core. Okay. Well,
Yeah.
core is not a feature we can exploit. We can directly access in our software. We can access thread indexing in our software. In our program, we can access the thread. We can create streams, that the topic we will be covering later. But we cannot, you can say, address the cores. Core addressing is not, this is not available in CUDA. Because I think that is purely hardware concept, maybe like that. For that reason, it's not like that's a direct addressing is not that is not available. Or maybe, probably I may not be aware of this. Let me give me some time. I will explore it. If there is something we can relate to the core in our code, I will check it out.
Yeah, maybe the streaming processors, right? If there is a way to group certain codes with certain streaming processor to a stream, and and then we can associate the kernel to a particular stream, then
Yeah, yeah,
maybe we can.
yeah.
Yeah,
That was,
I think that is what the team is trying to see.
yeah,
If how right now probably it goes to some default stream if we don't specify.
yeah,
So when we have multiple kernels we are launching back to back, they are probably serialized, right? Means unless we have multiple streams.
yeah.
So
Yeah. Then we have to handle multiple streams. Presently, all the kernel, if we are not specifying the stream, it is executing on the default stream only, which is zero number. By default, number is zero, and if we specify some number, that means it is executing on a particular stream. So that we will explore in later slides. Right. So should we continue ahead?
Vikram, another related question. So the number of blocks is fixed to the GPU card, right? The maximum number of
Yeah,
blocks.
maximum number is fixed. Yeah, yeah.
So what would happen if we give a number
High.
that's not supported?
Then we have to do it in error handling, basically. That we will
Oh, it just reports an error. Okay.
yeah, that will report an error, and that we have to catch, or we have to handle such kind of errors if there is any. Yeah,
Okay.
right. So as we discussed, I think this is again same thing. Thread blocks in the grid we specify in the first argument, and second specifies the number of threads in the thread block. Right. So regarding the indexing, thread blocks and grids can be made 1, 2, or 3 dimensional. We can pass this grid. It can be by passing a dim3 values. This is a simple structure defined by the CUDA with X, Y, and Z members. So we can specify the X index, for example. So CUDA card, whichever card you are using, there is in its specification, it is mentioned that what is the range of maximum value of X dimension, what is maximum value of the Y dimension, and what is the maximum value of the Z dimension. That is how many maximum blocks for X dimension, Y dimension, and Z. So all three multiplied together will be the maximum number of blocks which can be supported, and similarly for the maximum number of threads which can be in one block. So so in this case we have in this code we launch the kernel with thread blocks containing 250 threads. Our block is containing 250 threads, and we have used integer arithmetic to determine the number of thread blocks required to process all the n elements of the array. Minimum of 1 for n is equal to 1. Now, for the cases where the number of elements in the array is not evenly divisible by the thread block size, the kernel code must check for out of bound memory access. So, which is done by this statement. Means if our thread index goes, it may, but we have to check the bound that over indexing over this I or thread index is not accessing the element which is out of bounds of the array. So that is done by this statement. If I, that index should be n, less than n. N is our maximum number of elements of the array. So for these elements we are doing this operation yi is equal to a star xi plus yi. Now, last in the cleaning up, we have discussed earlier, that is, we have freeing the memory by using CUDA free for d underscore x, CUDA free d underscore y, free x, and free y. Now, regarding the device kernel code, a bit more detail about the kernel code. As we discussed earlier, identifier is underscore underscore global underscore underscore. Right. Variables defined within the device code do not need to be specified as device variables because they are assumed to reside on the device. So these arguments n, a, and I, which is defined inside the kernel. I is defined inside the kernel, and n and a are passed as arguments. These will be stored by each thread in a register, as we discussed earlier. Also, these will be stored in the register because these are the single element variables. Now, regarding the pointers x and y must be pointers to the device memory. The third and fourth arguments, these are pointer to the device memory address space. As we passed the argument d underscore x and d underscore y, that is d for the device. These are pointers to the device memory, which we created in the host code. We have passed these arguments to the kernel when we launched it from the host code. So the first two arguments, for example, these are n and a, these were not explicitly transferred to the device in the host code. These function arguments are passed by value. So these arguments, of course, n and a, these we are not passing its addresses. We are using pass by value technique for these two arguments, and for x and y we are using the technique of pass by reference, or we are passing their pointers or addresses. So CUDA runtime can automatically handle the transfer of these pass by values to the device. So this feature of CUDA runtime API makes launching kernels on the GPU very natural and easy. It is almost same as calling the your normal C++ function. So main in the in the kernel function we have mainly two statements only. The kernel is executed by multiple threads in parallel. If we want each thread to process an element of the resultant array, then we need a means of distinguishing and identifying each thread. That is, we have to now create the identity unique address of every thread, and that will be used for each array element.
Data types?
Just a second.
Okay.
Is it possible to do pass by value for some more complex data type?
Pardon?
Like the structure?
Vikram, the question was, can right now we are sending data types that are integers and floats, right?
Yeah,
And
yeah,
the
yeah.
question was, can data structure? That's what you meant, right?
Yeah.
Pardon? You want to
Pass by
transfer
value.
data structures?
Yeah, and if it can be passed through value, so pass by value and not.
Yeah, I think it is possible. I think it is possible. Data structure. Yeah, we can pass those. We can pass those by pass by value also. I think pass by reference also. We can pass their addresses. But we must know the technique, but how to access, address the elements in the device. Means we must decode it in the device code, that how to access its subsequent elements. Any data structure we are passing. If we are passing its starting address to the first element, or we are passing by value, then it is separate issue. But if we are passing by reference, then we must in the device write the algorithm to access its all elements, whatever the structure of our array indexing is. Right. Now I was just willing to go through this slide, just scrolling through this slide.